Could we ride a gravitational wave? It's a great question. It sounds like something from science fiction. A cosmic surfer catching a ripple in space-time and zipping across the galaxy. The idea is amazing. The image is powerful. But the answer, in short, is no. We can't ride a gravitational wave. And the reason why it tells us something fundamental about the universe and our place in it, it's not a simple engineering problem. It's a problem of physics, a problem of what we are and what a gravitational wave is. To understand why we can't ride one, we need to get a clear picture of what we're talking about. What is a gravitational wave? It's not like a wave in the ocean. It's not like a sound wave moving through the air. Those are waves that travel through a medium. The water is the medium, the air is the medium. The wave is a disturbance in that medium. A gravitational wave is different. It has no medium. The wave is the medium. It's a wave of space-time itself. Let's back up a bit. Einstein gave us this idea of space-time. He said that space and time are not separate things. They are woven together into a single four-dimensional fabric. Think of it like a giant stretchy sheet of rubber. This is the fabric of our reality. Now, anything with mass puts a dent in this fabric. The Earth makes a little dent. The sun makes a bigger dent. A black hole makes a really, really deep one. What we feel as gravity is just us moving along the curves in this fabric. The Earth isn't pulling the moon. The sun is curving space-time, and the Earth is following that curve. That's gravity. So what happens when these massive things move? If you have two black holes orbiting each other, they are stirring up space-time. They are like two heavy bowling balls spinning around on that rubber sheet. As they move, they create ripples that spread outward. Those ripples are gravitational waves. They are disturbances in the fabric of space-time, traveling away from the source at the speed of light. When one of these waves passes by, it changes the very shape of space. It stretches space in one direction, and it squeezes it in another. And then it reverses. It squeezes where it's stretched, and it stretches where it's squeezed. It's a constant pulsation of the geometry of the universe. This is the key. It's not that something is moving through space. Space itself is doing the moving. It is expanding and contracting, and that's where the problem of riding comes in. Think about a surfer on an ocean wave. The surfer is on a board. The board is a distinct object from the water. The wave comes, and it lifts the water up. The water pushes the board. The board pushes the surfer. The surfer can use their skill on the board's shape to stay on the wave's face, using the force of the moving water to propel them forward. There is a clear distinction between the rider and the wave. Now imagine a gravitational wave. You are in your spaceship. A gravitational wave comes toward you. As it hits, it starts to stretch space along a certain axis. What happens to you and your spaceship? You both stretch too. The atoms in your body get pulled slightly farther apart. The atoms that make up your ship get pulled farther apart. The distance between you and the front of your ship increases. Everything inside the affected region of space stretches together. Then, the wave squeezes space. Everything gets compressed. The atoms in your body get a little closer. The atoms in your ship get closer. The distance between you and the front of the ship decreases. You and your ship and the space you occupy are all doing the same dance. The wave is not a separate thing you can push against. You are completely embedded within it. You are part of the thing that is waving. There's no face of the wave to surf on. There's no force pushing you from behind. From your perspective inside the spaceship, you wouldn't feel any acceleration. You are, in the language of physics, in free fall. You're just following the path laid out for you by the curvature of space-time. In this case, the path is a wobbly, stretching, squeezing one, but you are moving along with it perfectly. There is no relative motion between you and your local patch of space, so there's no way to extract propulsion from it. You can't catch the wave because the wave has already caught you. It's like trying to pull yourself up by your own bootstraps. You can't do it because you and your bootstraps are part of the same system. You and a gravitational wave are part of the same system space-time. You can't use the wave to push yourself because the wave is also pushing, or rather stretching and squeezing, every single particle in your body and your ship in the exact same way. So, what would it actually feel like? Well, for the gravitational waves we've detected here on Earth, you'd feel nothing at all. They are incredibly faint. The sources, like two black holes merging, are a billion light years away. By the time the ripples get here, they are stretched out and weak. The effect they have is minuscule. The LIGO observatories, which first detected them, are L-shaped instruments with arms 4 kilometers long. A passing gravitational wave stretches one arm and squeezes the other by a distance thousands of times smaller than the nucleus of an atom. It's an astonishingly small effect. If a wave like that passed through you right now, you wouldn't have the slightest clue. Your body would stretch by an amount far smaller than a single atom. You are not sensitive enough to notice. But let's imagine we could get close to the source. Let's say we parked our spaceship a safe distance away from two merging black holes. What would it be like then? The answer is not pleasant. Riding would be the last thing on our minds. Survival would be the problem. Close to a cataclysmic event like that, the gravitational waves are incredibly powerful. The stretching and squeezing would be extreme. The forces involved are called tidal forces. It's the same kind of force that causes tides on Earth. The moon's gravity pulls a little stronger on the side of the Earth closer to it, and a little weaker on the far side. This difference in pull stretches the Earth and its oceans, creating the tides. Now, imagine that, but on a cosmic, violent scale. A strong gravitational wave would exert a tidal force on your body. The part of your body where space is being stretched would be pulled apart violently. The part of your body where it's being squeezed would be crushed. Let's say the wave is stretching space vertically and squeezing it horizontally. The wave would try to pull your head and feet apart with immense force while simultaneously crushing your shoulders together. Then, a fraction of a second later, it would switch. It would try to crush you from head to toe while stretching you out sideways. You would be torn to shreds. This is a process known as spaghettification. It's what happens when you get too close to a black hole, and it's what would happen if you were bathed in a powerful gravitational wave. Your spaceship would suffer the same fate. It would be twisted, torn, and ripped apart by the flexing of space-time itself. There is no material strong enough to withstand such a thing. The forces are not acting on the surface of the ship like a bomb. They are acting on every single point within the ship simultaneously. It's the fabric of reality itself that's becoming a torture rack. So, up close, a gravitational wave is not a cosmic highway, it's a blender. Far away, it's too weak to feel, let alone use. That seems to shut the door on the idea pretty firmly, but what if we think about it differently? Maybe we can't ride it like a surfer, but could we harness its energy? A wave is a form of energy, after all. Could we build a machine that extracts energy from a passing gravitational wave? Theoretically, yes, it's possible. Imagine you have two beads on a rigid rod, and the rod is floating in space. When a gravitational wave passes by, oriented in the right way, it will try to change the distance between the two beads. But the rod is rigid, so it resists. This resistance, this stress on the rod, is a sign of energy. Or, a better idea might be to connect two masses with a spring. As the wave passes, it squeezes and stretches the space between the masses, causing the spring to oscillate. You could then attach a mechanism to that spring to generate electricity, like how moving a magnet through a coil of wire does. So yes, you could extract energy, but the amount is again ridiculously small. For the waves we detect on Earth, the energy you could extract is barely measurable, far less than the energy of a single photon of light. It's not a practical energy source. What about close to our merging black holes? There, the energy is enormous. The merger of two black holes can convert several times the mass of our sun into pure gravitational wave energy in a fraction of a second. It is the most energetic event in the universe. Could we harvest that? The problem is the same as before. If you build a machine to capture that energy, the machine itself is subject to the same tidal forces. The incredible energy of the wave would manifest as a force that rips your energy harvesting machine to pieces. You are trying to dip a bucket into a tsunami. The tsunami will destroy your bucket and you along with it. So, the dream of a gravitational wave drive seems to die here. You can't ride it. You can't really harness it for power. It's either too weak to be useful or so strong it's destructive. This is where science fiction often steps in. Could there be some exotic material or undiscovered physics that would let us interact with a gravitational wave differently? Maybe a gravity sail? A material that is pushed by a gravitational wave instead of just being stretched by it? For this to work, the sail would have to react to the stretching of space-time differently than normal matter. It would need to somehow resist being stretched and squeezed and convert that into a net push. What would that look like? We don't know. It's not something that exists in our current understanding of physics. All known matter and energy are subject to the curvature of space-time in the same way. This is a core principle of general relativity. To build a gravity sail, you might need something like negative mass, a hypothetical substance that has a negative gravitational pull. Or you might need some way to anchor yourself to a different part of space-time. to give you something to push against. All of this is deep in the realm of speculation. It's fun to think about, but there is no evidence that such things are possible. There are other ideas for faster than light travel that involve manipulating space-time, like the Alcubierre drive. This concept involves creating a bubble of space-time around a ship, and then compressing space-time in front of the bubble and expanding it behind. The bubble itself would ride on this manufactured wave, potentially exceeding the speed of light. But this is not riding a naturally occurring gravitational wave. This is generating your own localized space-time distortion. And it has its own massive problems, like requiring vast amounts of negative energy, which we don't know if it exists or if we could ever control it. So where does that leave us with gravitational waves? If we can't ride them or use them for power, are they just a cosmic curiosity? Not at all. Their true value isn't as a vehicle, but as a window. For all of human history, we have studied the universe with light. We've used our eyes and telescopes to look at visible light. Then we built telescopes that could see other forms of electromagnetic radiation, radio waves, infrared, X-rays, gamma rays. Each new window showed us a universe we didn't know existed. Radio waves showed us pulsars in the cosmic microwave background. X-rays showed us matter falling into black holes. Gravitational waves are a completely new window. They are not light. They are a totally different phenomenon. They are tremors in the fabric of reality. And because of that, they let us see things that are completely dark. A pair of black holes orbiting each other emits no light. They are black. We could never see them with a traditional telescope, but as they merge, they scream out in gravitational waves. By detecting those waves, we can listen to the collision. We can know their masses, their spins, how they orbited. We are listening to the symphony of the dark universe. Gravitational waves also travel through things that block light. If a star explodes on the other side of the galaxy, a lot of the light might be blocked by dust clouds. But the gravitational waves from that explosion will travel straight through everything unimpeded. They carry a pure, unaltered message from the heart of the event. This opens up a new field, gravitational wave astronomy. We are no longer just looking at the universe. We are listening to it. We are sensing the vibrations of its most extreme events. We can learn about the insides of neutron stars, the birth of black holes, and maybe even the echoes of the Big Bang itself. These are things we could never learn about with light alone. There is another potential application that is a bit more sci-fi but still more plausible than riding them communication. Because gravitational waves pass through matter so easily, you could theoretically send a message with them that couldn't be blocked. You could send a signal straight through a planet or a star. It would be the ultimate secure long-distance communication channel. The challenges, however, are monumental. First, you have to generate a gravitational wave. We can't do that. It took two black holes, each many times the mass of our sun, spinning at near the speed of light, to create the waves we detected. To create a wave in a lab, you'd have to wiggle incredibly massive objects at incredible speeds. The energy required is far beyond anything we can manage. Second, you have to detect the message. The receiver would need to be something like LIGO, a gigantic hypersensitive instrument. It's not exactly a cell phone. The universe is also filled with a background hum of natural gravitational waves, so your tiny signal would be like a whisper in a hurricane. So, while it's theoretically possible, it remains firmly in the realm of far future technology. It's a very human question to ask. Can we ride it? It's a question about control, about exploration, about using the forces of nature to our own ends. We see a river and we build a boat. We see the wind and we build a sail. We see a gravitational wave and we want to build a surfboard. It's a natural impulse, but the universe doesn't always conform to our terrestrial analogies. Space-time is not an ocean. It's something much more fundamental. The lesson of gravitational waves isn't about how we can conquer the cosmos. It's about how we can perceive it. The discovery is not one that gives us a new tool for travel, but a new sense. It's as if we've been deaf our whole lives and suddenly we can hear. We are hearing the universe for the first time. We are hearing the thunder of colliding black holes and the chirps of dying stars. So, no, we can't ride a gravitational wave. The idea is a beautiful one, but it's born from a misunderstanding of what a gravitational wave is. Trying to ride one would be like a drawing of a person on a piece of paper, or trying to surf on a wrinkle in the paper itself. The drawing is the paper. It will just get wrinkled along with everything else. We are the drawings on the paper of space-time. When space-time wrinkles, so do we. The reality is, in many ways, more profound than the science fiction dream. We are not cosmic surfers. We are cosmic listeners. We are just beginning to tune our ears to the vibrations of space-time. And the music of the universe, which has been playing for 13.8 billion years, is finally becoming audible. We can't ride the waves, but we can listen to their story. And it's a story that is going to tell us more about where we came from and how the universe works than any joyride ever could. That is the true gift of the gravitational wave. It's not a new way to get around. It's a new way to understand.